Hi, today we'll be going through a calorimetry problem and a Hess's law problem. Let's start with a calorimetry problem. A chemistry student places 100 grams of copper at 80 degrees Celsius in a calorimeter with 500 grams of water at a temperature of 40 degrees Celsius. The final temperature is 40.71 degrees Celsius. What is the specific heat of copper? Water's known specific heat is 4.184 joules per grams degrees Celsius. Let's start off with what we know. So we know that heat flows from hot to cold. So the heat of the copper is going to travel to the surrounding water molecules because the copper has a higher temperature than the water. As the copper loses heat energy, its temperature will decrease, and as the water molecules absorb the energy, its temperature will increase. At the end of this, the final temperature will be the same. So for this case, the final temperature is 40.71 degrees Celsius. So now the first step you need to do is to find the change in temperature. And you do that by subtracting the initial temperature of copper and water from the final temperature of the system. You get 0.71 degrees Celsius change for water and a negative 39.29 degrees Celsius change for copper. We know that the heat released by the copper is equal to the heat absorbed by the water. One side has to be negative because the temperature of the water is going up and the temperature of the metal is going down. So to balance, you have to have a negative sign. Since this is temperature change, we can use the equation Q equals MCAT, where M is mass, C is the specific heat capacity, and delta T is the change in temperature. On one side, you have a negative MCAT, and on the other, you have positive. Now you can plug in. The mass of the copper is 100 grams, and we're looking for the specific heat capacity of copper, so we can use C as a variable. And the change in temperature of the copper is negative 39.29. The mass of the water is 500 grams. The specific heat capacity of water was given at 4.184, and the change in temperature of the water is 0.71. Now when we multiply, we get 3,929 C on one side and 1,485.32 on the other. Then we have to divide by 3,929 to isolate C and find the specific heat capacity of copper. And the specific heat capacity of copper is 0.378 joules per grams degrees Celsius. Now let's do Hess's law. Suppose you want to know the enthalpy change for the formation of acetylene, C2H2, from solid carbon and hydrogen gas. The enthalpy change for this reaction cannot be measured in a laboratory, but we can measure enthalpy change for the combustion of carbon, hydrogen, and acetylene. Use this information to calculate for the formation of acetylene from its elements. Let's start off with defining Hess's law. Hess's law says that if a reaction is the sum of two or more other reactions, then the change in enthalpy for this reaction is going to be the sum and change of enthalpy of those reactions. First, we need to start with the end product. But equation 1 only uses acetylene as a reactant, not as a product. So we can flip the arrow and write it as acetylene as a product. When you go from a reactant to a product, it releases 1,299.5 kilojoules, making it negative. But if you go the other way, then you'll need 1,299.5 kilojoules. So the delta H has to be reversed to a positive 1,299.5 kilojoules. So now we have something that ends up with what we eventually want to end with. Now if we want to get there, then we're going to need some carbon dioxide and water at some point. Then we can rewrite the other two equations because it gives us carbon dioxide and water as a product. Now we need to make sure we have everything we need. We need 2 moles of carbon, and here in the second equation, we only have 1, so we have to multiply the whole equation by 2, and the delta H by 2. So now the change in enthalpy of the reaction is going to be doubled. So now it's negative 787 kilojoules. Now we have to see if the sum of these reactions actually is the reaction from the beginning. Now we can cancel out reactants and products. So this equation produces 2 molecules of carbon dioxide, but then the 2 molecules is used up in the first reaction. So we can cross out the 2 CO2s. Now this reaction produces 1 molecule of water, and this first reaction requires 1 molecule of water, so we can cross those out. Now this reaction requires 2 molecules of oxygen, and this one requires 1/2 molecules of oxygen. So these two combined give us 2.5 molecules of oxygen. So we can then go ahead and circle those to give us 2.5. So those are the reactants, and in the end, those end up as products of the first reactant, because 5/2 is equivalent to 2.5. So they go into the system and then go out unchanged. So we can then cancel those out. Now we're left with 2 molecules of solid carbon plus a molecule of hydrogen, yielding in acetylene. So it is true that the sum of these reactions is what we want. Now we just have to add up the enthalpy values. We add those up to get 226.7 kilojoules, and it's endothermic because it's positive, so it is going to absorb energy.